Hey there, science fans! Have you ever wondered what makes up everything around us? I'm talking about the chair you're sitting on, the air you breathe, even that delicious pizza you had for lunch. It all boils down to incredibly small particles called atoms. Atoms are like the building blocks of matter. Understanding them is like having a superpower. It lets you understand how the universe works at its most basic level. Think of it like this. Imagine you have a giant Lego structure. What's it made of? You got it, tiny Lego blocks. Atoms are like those blocks, except way, way smaller. Let's take a trip back in time to see how scientists figured out what these tiny atoms are all about. Our first stop is with a brilliant scientist named John Dalton. He was a pioneer in the field of chemistry and physics, and his work laid the foundation for much of what we understand about the atomic world today. Back in the early 1800s, Dalton came up with a theory about atoms that revolutionized the scientific world. His ideas were groundbreaking and provided a new way to look at the building blocks of matter. Dalton's atomic theory basically said, 1. Everything is made of atoms. They're super tiny and indivisible, kind of like those Lego blocks we talked about. Just imagine the smallest piece of matter you can think of, and that's an atom. 2. Atoms of the same element are identical. Think of it like all the red Legos being the same size and shape. No matter where you find them, they are exactly the same, just like carbon atoms or oxygen atoms. 3. Atoms of different elements are different. Now, imagine blue Legos being different from red ones. That's like different elements. Each type of atom has its own unique properties and characteristics. 4. Atoms combine in simple ratios to form compounds. This is like combining different Lego blocks to build something new. For example, 2 hydrogen atoms and 1 oxygen atom combine to form water, just like snapping together different colored Legos to create a new structure. Dalton's theory was a huge deal. It was like finding the instruction manual for building the universe. Scientists were thrilled because it gave them a new way to understand how everything around us is made. But as with all good science, there was more to the story. Dalton's theory was just the beginning. Over time, scientists discovered even more about atoms, leading to the complex and detailed understanding we have today. The journey of discovery continues, and who knows what new insights the future holds. Fast forward to the late 1800s, and we meet J.J. Thomson, a scientist who made a shocking discovery. He found out that atoms weren't as indivisible as Dalton thought. Thomson was experimenting with something called cathode rays, which are beams of electrons. He realized these rays were made of negatively charged particles that were much smaller than atoms. Imagine cutting open that Lego block and finding even tinier pieces inside. That's kind of what Thomson did to the atom. He called these negatively charged particles electrons. To explain his discovery, Thomson proposed a new model of the atom, the plum pudding model. Picture a yummy plum pudding. The pudding itself represents the positively charged part of the atom, and the plums scattered throughout are the negatively charged electrons. Delicious, right? Thomson's plum pudding model was a step in the right direction, but it wasn't quite the whole picture. Think about it. If the atom was just a positive pudding with negative electrons randomly stuck in it, wouldn't it be kind of unstable? Like, wouldn't the negative plums all want to clump together? Good thinking. Scientists were puzzled by this too. They knew there had to be more to the atom's structure. And that's where our next scientific superstar comes in, Ernest Rutherford. Section 5. Rutherford's gold foil experiment, bouncing off the nucleus. Early in the 1900s, Ernest Rutherford, a former student of Thomson, decided to put the plum pudding model to the test. This model, proposed by J.J. Thomson, suggested that atoms were composed of electrons scattered within a soup of positive charge, much like plums in a pudding. Rutherford designed a brilliant experiment that involved shooting tiny, positively charged particles called alpha particles at a thin sheet of gold foil. These alpha particles were essentially helium nuclei, and they were expected to pass through the gold foil with minimal interaction. Now, if the plum pudding model was correct, the alpha particles should have passed straight through the gold foil with maybe a slight deflection here and there. The positive soup was thought to be too diffuse to cause significant deflections. After all, they were shooting tiny bullets at a soft, mushy pudding. The expectation was that these alpha particles would behave like bullets passing through a cloud. But guess what? Rutherford and his team observed something totally unexpected. They were in for a surprise that would change the course of atomic theory forever. Most of the alpha particles did pass straight through, but to their surprise, some of them bounced back at sharp angles. This was a shocking result that no one had anticipated. It was as if they'd hit something small and incredibly dense within the atom. This dense center was later identified as the nucleus, a compact region containing most of the atom's mass and positive charge. Talk about a scientific curveball. This unexpected deflection of alpha particles led to a groundbreaking realization. This experiment turned the atomic world upside down. It led to the development of the nuclear model of the atom, where a dense nucleus is surrounded by a cloud of electrons. Rutherford's findings paved the way for future discoveries in nuclear physics and quantum mechanics, revolutionizing our understanding of the atomic structure. Section 6. The nucleus is tiny but mighty. Rutherford's gold foil experiment led to a groundbreaking discovery. He realized that the atom wasn't just a mushy pudding after all. It actually had a tiny, dense, positively charged center, which he called the nucleus. Imagine a marble in the middle of a giant football field. That's kind of the size difference between the nucleus and the whole atom. Rutherford's experiment showed that most of the atom is actually empty space where the electrons whiz around the nucleus, kind of like planets orbiting the sun. Section 7. What about those empty spaces in the atom? Now you might be thinking, if atoms are mostly empty space, why doesn't my hand just go through my desk when I slam it down? Great question. Remember, those electrons are zooming around the nucleus in that empty space. When atoms come close to each other, their electrons repel each other like magnets of the same charge. It's this electromagnetic force that gives matter its solidity. Think about it. You can't push your hand through a wall because the electrons in your hand are repelling the electrons in the wall. It's like an invisible force field. Section 8. Beyond Rutherford, the quantum adventure. Rutherford's model was a huge leap forward, but the story doesn't end there. His model, often referred to as the planetary model, depicted electrons orbiting the nucleus much like planets orbit the sun. This was a groundbreaking concept at the time. As scientists dug deeper into the atom, they ran into some more mysteries that Rutherford's model couldn't quite explain. They observed phenomena that didn't fit neatly into the planetary model, leading to more questions than answers. For example, if electrons were orbiting the nucleus like planets, wouldn't they eventually lose energy and spiral into the nucleus, causing the atom to collapse? This was a significant problem because, according to classical physics, this should happen, but it clearly doesn't. It turns out the world of atoms is even stranger than we thought. The more scientists studied, the more they realized that the behavior of electrons defied classical physics. To understand it fully, scientists had to develop a whole new branch of physics called quantum mechanics. This new field provided the tools and concepts needed to describe the bizarre and counterintuitive behavior of particles at the atomic and subatomic levels. Quantum mechanics is like the rulebook for how things behave at the atomic level. It introduced revolutionary ideas such as wave-particle duality, where particles can exhibit both wave-like and particle-like properties. It's a wild ride, but the basic idea is that electrons don't actually orbit the nucleus in neat little circles. Instead, they exist in regions of space called orbitals, where the probability of finding an electron is highest. Instead, they exist in fuzzy clouds of probability. These clouds represent areas where an electron is likely to be found, but not with absolute certainty. It's like trying to pin down the location of a super-fast bumblebee. You know it's in the area somewhere, but you can't say for sure exactly where it is. This probabilistic nature of electrons is a fundamental aspect of quantum mechanics, making it a fascinating and complex field of study. Section 9. Atomic discoveries impacting our lives. So, we've gone from Dalton's solid spheres to Thomson's plum pudding to Rutherford's nuclear atom and beyond. That's quite a journey through the atom. But why does all this matter? Well, understanding the atom has revolutionized our world. It's the foundation for so many technologies we rely on every day. From smartphones and computers to medical imaging and nuclear power, our knowledge of the atom has led to countless advancements that have transformed our lives. Section 10. Keep exploring the atom. The quest to understand the atom is far from over. Scientists are still making incredible discoveries like the existence of even smaller particles within the atom called quarks. The world of atoms is full of mystery, wonder, and endless possibilities. So keep asking questions, keep exploring, and who knows what amazing discoveries you might make. Section 11. It's all about the atoms. From Dalton's indivisible spheres to the mind-bending world of quantum mechanics, our understanding of the atom has come a long way, and it all started with curiosity, creativity, and a passion for unraveling the mysteries of the universe. Remember, everything around you, from the smallest grain of sand to the most distant star, is made up of these incredible tiny particles. The atom is the fundamental building block of our universe, and its story is far from over.